Welcome to episode 4. Today I'm going to talk about a little bit of physics, and I want to introduce you to this beautiful image in the background. That's called the Crab Nebula. And what it is it's the remnant of a supernova explosion. So very massive stars, when they grow and they get to where they become too weak with their radioactivity to create enough energy to fight gravity, they explode internally. And this one happened in 1054. It lit up the sky like daylight. It was recorded in China. And this is the leftover part taken with Hubble. So why do I care about this? Did you ever wonder where all the stuff we're made of comes from? Our bodies, everything you touch, the Earth itself. I talked about the Big Bang, the creation of the universe. It didn't come from there. All that created was hydrogen, helium, and a little bit of lithium. And this is easy physics to figure out. It's not difficult. So the mystery was, how about the other stuff? And some guys about 30, 40 years ago figured out the only viable alternative was a supernova. So what that says is we must have had a half dozen or so nearby vicinity of the Earth. And that created these elements that condensed to form the sun and the Earth and everything else. So that's the idea of us really truly being stardust. I think it's kind of fun. So I'm going to talk about a little physics. If science is scary to you, there's not going to be any real equations you have to understand. So science is a little scary, you can skip on ahead. But I thought I might talk a little bit about how the thing kind of works. So physics is really describing Mother Nature through mathematics. And the king of physics, or the queen, let's say, is the experiment. If it disagrees with the experiment, it's wrong, no matter how elegant your theory is. So we do an experiment of some sort, and there's all kinds of things. I was an experimental physicist. And then we ask, what can we learn from what we see? And the most important thing is a first principle, which is the most fundamental, deepest knowledge you can find. And we express that often in mathematics. Then what we do is we call that a theory. And theory is misunderstood by lay people. Lay people have the idea, when you talk about, say, the theory of evolution, it's something your hypothesis you're not certain of. That's not what a theory means to scientists. A theory means to scientists a statement of fact that has been tested so many times that it's accepted as truth and is useful for predicting the future. So what's interesting is you can never prove a theory. You can only fail to disprove it so many times that it becomes accepted. And then we call it physics, settled physics, whatever you want to call it. So the field of classical mechanics was started by Newton in 1600s. Allegedly, he was in Cambridge under a tree and saw an apple fall, and he wondered why it fell straight down. And so he hypothesized that the speed of the fall was force equals mass times acceleration. And I think this was probably part of his thinking. You may know it about the same time he and Leibniz invented calculus. And so acceleration is a derivative in calculus, dv dt, velocity over change velocity over time. And then he went on to think about the fact that the Earth must be pulling the apple down. And I think this came from simple geometry. If you take a point source and illuminate, say, a sphere, the radiation intensity goes down like 1 over r squared. So he must have thought it's equal to how big the thing is, the masses times a factor, m1 into the mass of the Earth, mass of the apple, divided by distance squared. And this turned out to be very accurate formulation. And today we do many things with it. Almost everything in normal life, even for example, landing an astronaut on the moon, can be done with classical mechanics. So next came special relativity, and this is one really interests me a lot. So physicists from Newton's time up until 1880 reasoned by analogy. And I've talked about this before. This is sloppy reasoning, is lazy reasoning. We shouldn't tolerate it. What they did was they reasoned that since sound needed air to travel on it, and they knew that sound was waves of compressed air, they said there must be some similar thing for light, and they called it the ether. And two scientists in the 1880s, Michelson and Morley, went up on a mountaintop with a basic interferometer. And here's how the thing works. Light goes in here, hits a half silvered mirror, bounces off a mirror here. Some of the light bounces off a mirror here. And as you change the path lengths of this light, you will see fringes, light and dark patterns. So they put the thing on the mountaintop, and they knew that they knew for sure that the Earth is going around the sun. That was well-established science. They knew that the sun was moving in within an arm of our galaxy, and they knew the galaxy was moving relative to other galaxies. So they knew we had to be moving relative to something. So they made the measurement, and it was a complete failure in a physics sense. They found nothing. Well, Einstein took this and went to special relativity, and he did the first principle thinking. What he said was, if there's no ether, the speed of light in a vacuum must be the same all the time. It must be a constant. And then he did Gedanken experiments. He lived and worked in the post office over the train station. And he wondered what would happen when a train approaches the speed of light, and what would simultaneity look like, and all these things. And so he came up with a special relativity with this factor called the Lorentz factor. Here's what it looks like. It's a very simple equation. You take mass, length, or time, and you multiply it by this thing. This is your relative speed, and that's this constant, the speed of light squared. What was revolutionary about this is that people before this did not believe that time, mass, and length were relative. They thought they were constant, and he showed they're not. So that went on to the idea of, in my own use of this, if you're going to work with high energy physics, you've got to correct for the lifetime of particles by their relative speed to you in order to do the calculations for the kind of astrophysics I did. And so this is very well proven, kind of fun stuff. And what's important, I want you to get out of this, is how important the experiments are. Then came another fascinating experiment. I think this was in the 1920s. It was done many, many years ago in its basic form. So what you do is you have a light beam here, and you have a screen with two slits. And what you would think you would find is a bright band here and a bright band here. Well, people did this experiment long ago, multiple times, and they saw this. Now, everybody knew that electrons were particles. So they did the experiment with particles. This is the 1920s part. Did the experiment with a filament like the kind you have in an incandescent light bulb. Basically, the heat of the current going through the resistance of the tungsten filament boils electrons off, and light bulbs are partially evacuated. This experiment is done in a vacuum with a source of electrons like a light bulb has, or like an old, if you're familiar with the old tubes you used to have in electronics. And they were amazed to see this same kind of pattern, this interference fringe with electrons. And you can see this at any seaside. If you go see a breakwater someplace where there's two holes in it, you'll see the same pattern on the shore of the breakwater. So that they kind of thought, well, that's kind of interesting. That means that electrons act like waves. And they were pondering that. A more sophisticated experiment sent electrons through the slits one at a time, and they could see an electronic detector on the back, the spot on this phosphor where each electron was hitting. So it's absolutely certain these are particles. You see one by one electron hit, and they couldn't interfere like light does because they're not going at the same time. They're going separately. They were certain they would see these two bright fringes, and they said they saw the same interference pattern. This led to the idea of what's called the wave-particle duality. This went on to lead to the field of quantum mechanics. That's the central equation of quantum mechanics, the Schrodinger wave equation, in a very simplified form, with this H being an operator, the Hamiltonian, which is total energy of the system. Psi is the wave function, and these calculations are doable. I did them in undergraduate school. And if you want to understand even something as simple as a transistor, it's impossible without quantum mechanics. And this theory has been tested to n decimal points. It's interesting in that it's just like much of physics. When you get to extremes, it confronts directly your intuition. but scientifically it's correct. And then came general relativity. So Einstein did this work about 1905, and it took him 15 years later. And he pondered what was there any difference between the force you would feel from F equals ma from an accelerating, say, room with no windows, or the force of gravity down here. And he concluded that they were the same, and this is enshrined in a name called the equivalence principle. Once again, he did Gedanken experiments, and the one that I'm fond of is he took, imagine you were in this room, and there was a light source on one side, and you're accelerating constantly, which means you're going faster and faster and faster. This is not it's not practical in reality, but is a thought experiment. And he knew that the light speed was finite from over here. He knew what it was. And what that meant is light coming out of this side of the room, because it's accelerating, would hit the wall of this little hidden room further down, because it takes time for the light to travel across here. And by the time the light has traveled here, the room has moved. So this led to, this is called the field equations. It's very complex to solve. Excuse me, to solve these little UV indices here are X, Y, Z, and T, the three coordinates of space and time. And these are Riemann tensors, and it's all very complicated, but people can do this, and made some interesting predictions. The first one to be tested by Sir Arthur Eddington in about 1913, I believe, was the first test. And what this predicted is light would bend. So what he saw was, in his little Gedanken experiment, the beam of light in an accelerating frame would bend. And he concluded, therefore, light experiencing gravity would bend. So they went and waited for a solar eclipse, and they had certain bright stars up here, and they plotted them. And they had Einstein made predictions about how the sun would bend the light as the light came past the sun. And of course, you could only do this during a solar eclipse because you had to block out the sun to see these stars. And sure enough, Einstein had it right. And then that predicted something called gravitational lensing, which said that if you have light coming from throughout the universe, say this is an emitter, and there's a massive object in between, it can make the light appear in multiple places. And Hubble sees gravitational lensing routinely, and you can calculate some interesting math things in that with this. But most recently, 100 years after Einstein did this work, some friends of mine, led by an MIT guy named Ray Weiss, got a Nobel Prize for measuring gravitational waves. And what Einstein predicted was the gravitational masses orbiting together would emit gravitational waves. Now, of course, the only thing, it's very difficult to experiment. The mirrors, excuse me, had to measure displacement distances over kilometers of a small fraction of a hydrogen atom. But smart guys did this experiment and verified gravitational waves exist. So I could do more of these, but these are my favorites. And what I like about this is the simplicity of the experiment leading to the complexity of the science. And that's how it works. So that's basic physics, how it works. So I mentioned when I was looking at the fourth turning, I wondered about what was the grounding and basis of the 4D system, and how solid was it in terms of first principle thinking. And I've talked about the fact that I spent a summer and I got the idea that the business books must be useful. That was wrong. And I got the idea that if I took the things that are the 2, 3, 4, 5, 6, or 7 things you do and put them on the wall in my office, I could find a unifying principle. Physicists hate lists. We like principles and equations, organizing systems, and discovered in this process, a little bit longer story I'll explain later, an organizing system that analyzes social things. What does the word analyze mean? It's a physics word that means simplify. And I'll show you how this works later. But this then in turn led me to build at least 4 important things to help people have better lives, better leadership, and better teams. This is a workshop in China. I've done maybe, I don't know, 300 or 400 workshops over the years I've been doing this work. This is a funny picture because in China they like to put up a big image of me behind the screen. Here's their work in Chinese. This is a behavioral measurement tool that turned out to be arguably the certainly the biggest discovery for me of this work. And what this tool turned out to do, and I'll show you evidence later, it improved team performance an average of 4% every time you used it. It takes 10 questions and 15 minutes to do. So this is a remarkable finding. This is the context shifting worksheet. I'll explain this later too. So I wanted to be able to think differently about problems, particularly as a consultant. And I invented this, and this works very effectively. You can take an unsolvable problem and solve it in an hour. And lots of people are doing this. It's a very beautiful process. And then in 2009, Wiley published my book about all these things, which has been a lot of fun for me. So that's the basic story of how I did the 4D system. People ask me, how'd you do it? I said, well, it's just like you do all physics. You take data and you get perplexed by it and you try and find a rule, a system of thinking, equation to help you explain it. And that's what I did. It's not that hard if you're trained this way. And there we are. So that's going to end this little YouTube video. Hope you enjoyed it. The next one's going to deal with some other core concepts that I think are the underpinning of this work. And hope to see you next time. And be safe. And thank you for watching. Bye-bye.